together a totally arbitrary sequence, and I was going to ask Carl Lazarus if he could start off.
Okay, and I'll see what I can get into 10 minutes. I could easily take longer, but I'll give it a start.
This is a perfect example of where I thought it might create a much longer discussion.
Yes. So I know you and I had talked about that I would say something about Iron Mountain, but once I started really thinking about it, I realized that I had to go back to a previous stage. So in at the beginning of 1996, I joined a startup company called Connected Corporation. I was the seventh person there. It was formed to do online PC backup, something that was quite new at the time. I think some company had done a little bit of that with the Mac. I don't know that we found anyone who was actually doing it on Windows at the time. And I joined a few months after the company had started. They were busy developing the software at the time, and I was hired to be responsible for what was called operations, which in practice was pretty much everything other than selling or marketing or finance. So it meant being responsible for the network, such as we had at the time, which started out with a 10 megabit per second Ethernet. We were providing this backup service. We were going to provide a backup service that would, where we would run servers and tape libraries, and our software running on a user's PC would connect up to us. Internet was in existence at the time, but still most people and small businesses didn't have it. Now, this was a time when AOL was probably the king of connectivity. So we set up an arrangement with some company whose name I forget now that had something like AOL. They had access points in a lot of places, and they had a dialer that they were willing to license. And so we set it up so that PCs would back up to it. The original business plan was developed after a little bit of a survey, and I have no idea now why that survey produced the results it did, that said that, gee, lots of small businesses and individual home offices and the like would love to have a way that automatically backed up everything on their PC so they didn't have to worry about it. And we did come up with a service that did that. And we really didn't have a lot of capital behind us. So there was a little bit of venture capital. It was really tiny by today's standards. And so we didn't have anything to do advertising, but what we were going to do was send out a mailing of diskettes, very much like what AOL was doing at the time. And we got some mailing lists of what seemed to be small businesses. So it was thought particularly that little law offices and dentists and the like would use this. Well, it turned out that when we actually finally did our mailing, when we had set up our servers and were sort of ready to go, that the response was pretty much crickets. And so I think it really came down to that people who had never heard of us thought that maybe it was a good idea to get their PC backed up, but weren't that comfortable about sending their stuff out over to be stored someplace else. We really got sort of nowhere with that. Oh, I should mention, one of the interesting things that I had to do was we had this idea of that we were going to store everything in duplicate at 2 different sites. And this was really just before like internet data centers were coming around. And so we actually had one data center was in the offices that we occupied in Framingham. And then I found another location at the other end of Framingham where we could also set up a little data center. By the way, these tape libraries were massive. Moving them in was quite a job. And then establishing a data line between them that we could use, that our software would copy everything as it was received over to the other site. So eventually, this business model failed, and we switched to going after larger companies. And the idea was to sell them on backing up all their employees' PCs. And we had a modest amount of success with this. And Harry, I have to tell you that BB&N was one of our early customers. So I don't know, maybe you saw this, saw our software.
I wasn't in that end of the business because we had, an IT department that certainly must have been doing all that stuff, and they were set apart from us by a long distance, so we wouldn't mess around with it.
Well, anyway, I have to say that, so think of backing up your computer over some sort of dial-up connection, which seems like would be absolutely impossible. But first, at the time, most people didn't have that much on their PCs. So it was certainly, there wasn't going to be video on there. There might not be any pictures at all. Digital cameras, I think, had not yet quite cracked the 1 megapixel barrier. And we're not in that widespread use. So mostly what we were backing up was documents of various sorts. And the idea was that the first backup might run for many hours, and it could be interrupted and it would pick up again. But then the software was very good at the PC end at figuring out what had changed since the last backup and being very parsimonious in what it transmitted. So, it did data compression, but also did things like, we had this thing called send once, that, if you saved a file under another name, we would recognize that we already had it from you. And in fact, and if your file changed, we only backed up, we found changes in the file and backed those up. So overall, that made, the purpose was to make the backup as small as possible. And I think mostly we succeeded at that, but the business really didn't do that well. So even when we changed to this having salespeople and selling to larger companies, most of them that signed up with us didn't actually just automatically implement it on all their PCs. They sort of made it available. IT directors generally were of the opinion that it wasn't their responsibility for the user's PCs. They didn't want to own that responsibility. And so they said, here's something that you might want to use. Of course, we really want you to save everything on a company file server, but most people actually had some important stuff on their PCs. They didn't have everything on the file server. So we sort of went along with sort of modest success. Oh, by the way, when we started out, we had software for Windows 95, which was which had come out already, but was still gathering momentum, and Windows 3.11. So we dropped that after a little while. And eventually we made use of the internet. So overall, I think we were too early people were just not ready to, the whole idea of sending your stuff out into the cloud, which is now widely accepted, was looked upon with great trepidation at the time. And, we certainly spoke with many company IT directors who said, oh, I would never send anything out of our premises. Of course, by the way, they sent backup tapes to companies like Iron Mountain all the time, but somehow that didn't count. Anyway, eventually, the company was sold to Iron Mountain. And it was, we had several rounds of venture capital. So it ended up with the venture capital investors really got most of the money from that. And those of us like myself who had equity in the company did okay, but it was a base hit. It was by no means a home run.
Let me ask Bill Halley, who's new to the group. He's a friend of mine from Raytheon, going back to the, I don't know, middle or late 80s, and recently retired. And he may actually remember who we used to back up all our Sun workstations where we had all our mechanical systems. But it was an external company, but I don't remember whether it was yours, Carl. So, Bill, you want to take over?
Sure. Yep. Hopefully you can hear me. I'm going to talk about how I met John Rudy. So, and I went to Lowell Tech as a mechanical engineer, and I actually took one of the first solar engineering courses that they had, it was taught by a nuclear engineering professor. But I basically started off at Raytheon. At the time, there weren't a lot of jobs. This was 1977, 78. And so it was kind of an interesting time to get a job. But I went to Raytheon and I worked there the whole time. I was very lucky. I had some really good bosses. I started off my journey in computers. I figured I'd talk about that here because it's the computer club. I bought a Radio Shack TRS 80 computer in 1979. And I talked to my boss about it and I said, hey, I just bought this thing. And he remembered that because a couple of years later, Raytheon upgraded their computer vision CAD system from CADS 1, which was basically a 2D drafting system, to CADS 3, which actually lets you do 3D wireframe and then surface modeling. And so I was one of the first, I was in the first group of engineers that did computer vision CAD training. And I really liked it. I was lucky enough to get assigned to a job that basically for a whole year, I just did layouts with another designer on a CAD terminal where we laid out what it would take to package a radar system into a missile silo that after an initial strike, this radar system would pop up out of the silo and then take over for probably what else got destroyed in the first strike. The way Raytheon had their mechanical engineering group, they had design engineers, and then they had an analytical section. And the analysis folks did all the verification of everything that we designed. And originally it was done a lot by paper, manual calculations, and then Nastran came in. But modeling complex shapes in Nastran was quite difficult. You basically use punch cards to define your model. And WPI had worked with computer vision to come up with a way for us to map finite element models onto a surface model. So I did that for the antenna portion of this design. And we gave that to the analyst. And that prompted a visit from the section manager of the analyst, where he suggested that I stay out of their strawberry patch and stay in mine and let them do all the modeling. So that was kind of interesting. It's since changed a lot since then, but we then upgraded to CADS 4, And at about this time, Raytheon was split up into a bunch of different divisions: equipment division, missile systems division. And I think, John, you were part of missile systems and I was part of equipment division. But they had a few corporate groups that met and tried to coordinate systems like the mechanical CAD system, electrical CAD system. And that was called RayCAD. And that's where I met John. And we would meet, I don't know, monthly or so, just to make sure there was an MCAD group and make sure that we were kind of using the same equipment so we could share resources and share personnel. And also deciding standards, maintenance agreements, what was the next tools we were going to look at, you know, where we're going to switch from computer vision to something else. And then about 1990, I became manager of the MCAD group. And so, which was kind of fun. We were still using computer vision, but we were also looking at what the next generation systems were going to be. And one of computer vision's competitors, PTC, Parametric Technologies, found out about this, and they wrote a letter to the president of the company telling them that if we didn't pick their tool, we were the dumbest committee that they had ever been. And evidently this was a strategy of PTC's, but in some cases it worked, but luckily in Raytheon's case, it did not. The letter was intercepted by the vice president of engineering at the time. And we basically wrote a letter back to PTC saying we would never pick their tool, that no matter what, that, you know, we pick tools based on technical merits, not letters from president to president. Then Raytheon merged with TI and Hughes, their defense contractor sections. We also, just a year or two before that, we merged the equipment division and the missile systems division. So all that work done by RayCAD to make sure we were kind of on the same page really helped, because we were able to easily merge our people and our tools. But TI and Hughes, they happened to use PTC for their tool. And at the same time, right around the exact same time, PTC actually bought computer vision. So we ended up using PTC's tool eventually. Computer vision's tool hadn't been upgraded in a little bit. It wasn't as robust. So we went on a very big, long spree of, training people. So, but in the meantime, continued to work with John and the RayCAD group, and make sure that, you know, we all use similar tools and everything. But I'm not sure how much. I think it's spent about 10 minutes, but that's basically a little bit of the history of mechanical CAD inside Raytheon, as well as how I got to work with John.
I think one of the interesting things that came out of that whole experience is that when you have a large company, it's really, really easy for every piece of that company that's fundamentally doing basic engineering. You know, they all need the same capabilities, and each group on its own would come up with a different solution. And one of the things we found at Raytheon is that it was fairly common for one division to run out of people to do something, and they'd contact the other division and say, well, can you have a few people help out on something? And if the systems were totally dissimilar, then it was just chaos. So it was a valuable lesson for uniformity, even though it was really fought against in many cases.
Yes. Yeah, as a matter of fact, I got to go to Beach Aircraft, which Raytheon owned at the time, and they had fallen behind, and the FAA was going to actually pull their certification because they weren't keeping up with change orders in the documentation of the aircraft. And the people at Beach, they used CATIA and some other tools, and they weren't happy that we were being kind of forced down their throats. So they decided to give us the drawings from their Mitsubishi aircraft that they had licensed from Japan. And we got a whole bunch of drawings that were actually in Japanese that we had to modify. And so we got them scanned in, and we ended up modifying them on our CAD system. But that was quite an interesting experience as well.
Mike Alexander, can you take the next chunk?
Sure. Okay, what I'm going to talk about is something from graduate school, actually. A couple of things, depending upon how time goes. And this is, you might say, adventures with liquid helium. Not research in liquid helium. That's really pretty esoteric stuff in a way, but just trying to use it and transfer it. So I thought I would talk a little bit about what it was like when I first started using liquid helium. Now, for those of you who have not used it, it's just a colorless liquid. It's very cold. In fact, I've always been amused at listening now to this discussion about keeping the vaccine super cold with dry ice. Dry ice is at 195 degrees above zero, above absolute zero. I'm going to speak only in Kelvin. Above absolute zero. That's 195 degrees above absolute zero. Liquid nitrogen, which a lot of you have encountered at least when you're being blasted by a dermatologist with the vapor, is at 77 degrees Kelvin. So that's a lot below. And what we're going to talk about, or I'm going to talk about, is 4 degrees and going down to 1.5 degrees, more or less, Kelvin, above absolute zero.
Maybe you can explain how they can get anything that cold.
Well, I'll talk a little bit about some of that, but not about how it's manufactured, which I have guesses about based on my experience, but I have, to me, it was just something that you got out of a can, out of an insulated can. So what I would do, I had experiments in which I wanted to operate first at liquid helium, that is normal liquid helium temperature, 4.2 degrees, and then at 1.4 degrees. Now 1.4 degrees was as cold as I could make the system. The way you do that is that you have a giant vacuum pump, at least giant for those days, and you pump on that helium. When you lower the vapor pressure, you lower the temperature. And so what I would do is I would do my measurements at 4.2 degrees with my sample, in effect, in the liquid helium throughout. A little more complicated than that, but that's basically what it was. And then for the lower temperatures, I would turn on this big pump. And I would use what we call a U-tube. It's like a thermometer. It's like a, it was filled with some vacuum pump oil, and you put the one end is open to the atmosphere, the other end is open to the pump, so that as you evacuated things, as you pumped on things, and it got colder, the oil in the tube would no longer stay the same on both ends because it would be compressed by room temperature. And you could use that sort of to monitor temperature. I didn't use it to measure temperature, but it was a way of seeing what was going on. So we would pump down, and we'll go on, and then you reach a certain point, which is at 2.17 degrees, and there's a phase change in the liquid helium. Now, this is all well known. I'm not doing any new physics in this discussion. But what happens then is that there's a change, it's a phase change, which is not the same kind of change that you have when water turns to ice or something like that. It's something in the ordering of the liquid. After all, you have a liquid first to start with. And the liquid goes to what's called a superfluid phase. It's very much like superconductivity. In fact, people used to draw a lot of analogies to it. When we would hit that point, the liquid, which had been bubbling because we were removing helium gas as we pumped on it, I could look at it in the flask that we had. It would suddenly begin to bubble like crazy. It was almost looked like it was going to jump out of the flask itself. Much stronger than anything else. You know, if you overheated a pot of water and it's boiling over, it was even stronger than that. And well, okay, I hung on for dear life the first time. Later on, I realized this is what was normal. And then all of a sudden, it stops just almost instantaneously, and it's absolutely quiet. Not even a little bit of bubbling. I can't see where the surface is of the liquid helium. I wonder whether I'd run out of liquid helium. But in fact, what had happened is that we'd entered this so-called superfluid stage. There's now there's a heat of vaporization that goes on with this specific heat change. And what's gone on, and I'll get more to it on the way back as we come up in temperature. But anyhow, I could ordinarily, like most things, if you look at a tube of water, there's a meniscus. You can hold it up and you can look and you can see where the level is from that meniscus. There's no meniscus. It's just dead flat. Eventually, I figured out how to see it and convinced myself that I still had liquid helium. And then I would keep pumping until I got to 1¼ degrees and do the experiment that I had to do that day. They usually lasted hours. And then finally, we finished and we got to get rid of the liquid helium. You can't just open it all up because to expand, it's going to expand by factors of hundreds. The ratio of 4 degrees to 273 degrees. No, actually, yeah, one degree actually at that point to 273. You can't let that happen all at once, so you have a very big explosion. So you just let the system kind of on its own warm up. And as we're doing this, I'm watching that YouTube, and I'm seeing things glow. That's how I sort of can monitor where the temperature is. And the temperature is increasing and increasing a little bit and a little bit. And then it gets to the 2-degree point and it stops. And nothing's happened. And first time, well, and even later times, I wondered, holy cow, what's going on? I got to get home. You know, it's late at night and I haven't had dinner. And my wife's been working all day. But I got to stick with it. It just sticks there and sticks there. And what physically is happening is that there's this big spike. If you graph the heat capacity of the system at 2.2 degrees, where the system has gone into the superfluid stage, there's an energy involved in that. And it's a huge energy. Well, it's not a huge energy, but it's all concentrated right around that 2.2 degrees. And so the system sits, and it sits, and it sits. And you wonder whether the damn thing is ever going to warm up. And then, finally, you begin to see it. The temperature begin to go, not too fast. Can't afford to let it go fast, but it got past that point, and it behaves like a normal sort of thing. That's the first story. The second story is the liquid helium story also. It has to do with the fact that we think that it's infinitely cold down there. Or for that matter, the liquid nitrogen is infinitely cold. When I first did these experiments, as I said, I had everything plunged into liquid helium. First, you would have it at a liquid nitrogen temperature. You have a liquid nitrogen flask which surrounds the liquid helium flask, and both of those flasks are silvered except for a little spot area where you could see it. That's how I was able to view the liquid helium. Now, part of the liquid helium flask had gotten broken in somebody's earlier experiment, and since my professor wanted to save money, he didn't want to buy a whole new system, so he went to the glass shop at Cornell, and which could not do the silvering, so they put this tip on it, and with that tip, then welded on, then we would have to have the liquid. We would have the liquid helium. So the liquid helium was in, you might say, a half silvered system, and it's surrounded by a door of liquid nitrogen. Now, why is that door of liquid nitrogen there? Well, it's there to give you a cooling so that the system isn't exposed to room temperature. Well, I found that the liquid helium, I was new now in the graduate school, in the lab, and I would transfer the stuff, and it would last about 4 hours. The previous graduate student, who had since left, had run experiments for 8 hours or longer, doing what I thought was exactly the same thing. Only he'd had the original intact door. And I wasn't really thinking about that, and neither was my professor, who was, I think, beginning to think that because I could only make the stuff last 4 hours, that he must have this incompetent new graduate student. And I tried one way after another, and all I did was blow off liquid helium after 4 hours, when it usually took me about 8 hours to do the entire experiment. So I was getting nowhere. And then finally something dawned on me, and it was, you might say, a Hail Mary type of path. And this is something that Charlie ought to recognize, and Carl, when I get to it. I thought to myself, hey, this liquid helium at the bottom of the door is looking at liquid nitrogen. There's a thing called, and now I'm blocked. Sort of, it's a radiation law. It's called the T to the fourth law.
Stefan Boltzmann black body.
Right, black body law. And I said, T, could that be what it is? And, and of course now I was realizing why that nitrogen door was around it altogether. Now the Stefan Boltzmann information was really calculated for two infinite planes. And I was dealing with a one door around another. But being like a physicist, I thought one cylinder around another is like an infinite system. So I did the calculation about how long the liquid helium, I had to find out what the energy was that was required. And here I am thinking that I'm dealing with two infinitely low temperatures. This is an impossibility. And I calculated how long the liquid helium should last when it was exposed to, and I had the dimensions, certain amount of radiation from liquid nitrogen. Okay, now those of you who are not used to this, you can just think of opening up your screen door, your storm door. This is what I do to warm my house a little bit. And you can warm your house by solar heating, right? This is solar, like solar heating, only it's from liquid nitrogen temperature, from 77 degrees Kelvin. And damned if I didn't get the right number for what I was seeing. Within, I don't know, I forget. It was close enough. So I took it up to the professor, and he looked at it and he said, I guess I better buy a new door. And I got the new door, and I was able to make liquid helium last 8 hours, and I was able to reclaim myself, and I guess, in his eyes. And I finally got out with my degree. And that's his story.
Well, I'm glad you graduated.
So am I.
Well, thank you. Any questions on that before we move on to I don't know, Dick Wagner?
We should sometime, Mike, we should show, I mean, there are videos of helium going through that lambda point. We should show one sometime.
Yeah, it's quite exciting.
Well,
To a physicist, watch out about that.
No, I mean when the first time that happened, I was afraid I was going to lose my equipment. It was just going wild.
well, of
Why
course,
don't you-
everybody knows we've got potpourris about every 5 weeks or so. So that's where there's always an opportunity to expand on some of this stuff. So
Well, maybe Charlie can look it up.
if you
Sure.
find something good that you want to show,
Why me?
just let me and Steve and Peter know, and we'll stick it into to a potpourri where we have time. Although I think our potpourri list is getting longish once again. Thank you.
You guys can fight over who wants to find a video.
I have a feeling Charlie already knows.
Dick Wagner, are you there?
I'm here. John, with your indulgence, since I'm not an engineer, what I was going to do is go through my professional history and give you some highlights from it. And then maybe from that, if you want something more detail on some things, I can talk about that. Because it's going to take probably 10 minutes anyway to go through the history. There's lots of things that happen historically with me. So if that's okay with you, that's what I'll do.
Sure, why not?
Go for it.
Okay. Okay, I started off in mechanical engineering. After 1 year, I switched to electrical engineering. After my second year, I switched to physics. I went on for a master's in physics, and I had an assistantship from a glass company to do research for them. The research was done X-ray spectroscopy of germanium dioxide. Now, germanium, as you all know, was a substance back in the days when solid-state physics was really going, and that's when I was doing this. It was very important for electronic work and so forth. Germanium dioxide exists in 3 physical forms, 2 crystalline and 1 amorphous. Thus, that's why the glass company was interested in it. So for my master's thesis, I did the X-ray spectroscopy, and sure enough, the 2 crystalline forms showed different kinds of structure in the spectrographs. In the amorphous form, we also saw structure. So I think for the first time, we were the first ones to show that an amorphous substance could have structure. There were theoretical basis for these before. It was known and probably was recognized that this was second and third order structure. Not all amorphous substances probably have this, but at least germanium dioxide amorphous does. When I was an undergraduate, I had to take ROTC because I went to a school where ROTC was required for the first 2 years. I decided, even though physicists could get deferments when they were drafted, I decided that I didn't want to take the chance that I wouldn't get a deferment. So I decided to go on for the other 2 years of ROTC. So I got my commission and then I went into the military. The drawback for doing that is that you must serve in the military if you go on for the second year, if you're a commissioned officer. Fortunately, the physics background helped me because then I was assigned to a group that worked with nuclear weapons. And we had all the nuclear weapons that the Army, Navy, Air Force had at the time. So I was in that group. At the time, I decided to go on for a PhD. And I saw that physicists were doing a lot of work in molecular biology. We're beginning to do work in molecular biology, making real breakthroughs in molecular biology. So I decided to go on for a PhD in biophysics, was just starting programs at that time. I decided to go for a PhD, for a department rather than a program, because a lot of physics departments had programs, but you had to go along with what their requirements were for the PhD in physics. I wanted a department that was strictly going to go brand new into biophysics. This department turned out to be rather rigorous. All of us graduate students, most of us having masters in physics, had to take 1 year of organic chemistry at the level of the chemistry majors. We had to take 1 year of biochemistry at the level of biochemistry majors, and we had to pass the minor exam. We had to take one course in graduate level biology, whatever course or subject that was. The people who came into our department from physics or from biology departments had to take physics through quantum mechanics. My PhD thesis there was in electron spectroscopy. What we did is we chose a molecule that is a chromophore of most proteins. And if you look at the organic structure of that molecule, there's certain things that you see in it. So we took a group of molecules of this type, and by making strategic changes in the atoms and the atomic locations, we could get to a chromophore that's found in all nucleic acids, or at least most of them. Very few that don't have this chromophore in them. So I did both theoretical, that is quantum chemistry, and actual spectroscopic measurements. There was nothing that was great that came out of, I mean, nothing earth-shattering that came out of that. But what happened about 3 years later, I saw a paper in organic chemistry where they had taken one of the molecules that I had studied theoretically and showed that they were getting an attachment, a chemical attachment at a site that nobody ever expected could happen. I took a look at that and I said, aha, the reason is because the first excited state of that chromophore has a lot of charge attached to that area. So it turns out that electronic states, excited electronic states, are important in chemical reactions. And today, that's something that's going on quite a bit. You see this all the time, but I didn't recognize it until later, and I had that aha moment. After the PhD, I decided to go on for a postdoc. I got an NIH fellowship, and I decided I wanted to study the brain. So there was a technique that was just starting at that, or not just starting, it had been around, but it's just beginning to expand, called cell culture. In cell culture, what you do is you take a piece of tissue from an organism, including a human. You separate the cells into single cells, and then you put them into plates or you put them into bottles and you let them grow. So I was able, with that postdoc, I was able to grow neural tissue, that is neurons and glial cells and connective tissues in culture. After the first year, Richard Nixon, his infinite wisdom, cut off all the support for fellowships and assistantships for NIH, and I think for NSF too for that year, because graduate students and postdocs were demonstrating against the Vietnam War. Fortunately, there was a person in that area whose group was working on platinum compounds for cancer chemotherapy things. This was pretty startling that platinum could have a cancer chemotherapeutic effect. So I went into that group, set up a cell culture area, and working with, collaborating with an electron microscopist, we were able to show where in the cells the platinum resides. After that year, I decided that I needed to learn more about biochemistry. So I used my NIH fellowship and went over and learned biochemical techniques, particularly in zymology. I set up a cell culture lab there. It worked on neurons. And one of the things that happens is you're working with fewer cells. So it's difficult to get measurements that you can really read. So I started to learn how to do amplification techniques, you know, playing tricks to amplify the things you could do. Nothing really great came out of it. I mean, I learned a lot, but it wasn't too big there. I decided, since I liked the brain, I wanted to learn embryology. So I went to probably the most prestigious embryologist on brain science and did a postdoc with him. Did some experiments where you see in developmental biology how one tissue affects the other. In other words, the timing and the position of where things grow and how they grow. This person decided to take a department chairmanship at a university that's 3,000, 4,000 miles away. And I didn't want to go with them. I could have, but I decided not to. In that department, though, there was a big group working on cellular communication. Now, when cells communicate with each other, they do it in 3 different ways. One is when cells attach to each other, in other words, contact each other, both cells send lots of signals to each other through that contact mechanism. Lots of stuff that goes on biochemically. A second way that that's happened or the communication occurs is what we call humorally. That is, cells will put out molecules into the humor, into the bloodstream, into the lymphatic system, into the extracellular space. Those molecules go to a target site and cause a reaction. So your thyroid, your gonads all have this effect. Hormonal effects are big. I mean, you all know about those, I think, pretty well. The second way that it's done is through the synaptic cleft. In other words, neurons will send signals through a cleft to a target neuron or to a target cell, target muscle. But the third way wasn't well known. We weren't the first ones to see this, but it wasn't well known. So we worked on that. And that's a situation where the cells, when they attach to each other, they actually form what are called gap junctions or pores between the cells. And this allows larger molecules and materials to pass from one cell to another. Things that are in the exterior, the extracellular space do not get into those areas. So there are pores, pretty good sized. And what I was able to show that in a model system that embryologically, that communication pathway system changes over the embryological development of whatever the tissue was. We had a model system, so that's what it was. And so I was able to show that that was taking place. Obviously, I'd been postdoc for a while, so I decided I better get an actual job. So I got an academic position, and this was in a radiology department of all places. But they were doing lots of research. So I set up a cell culture system there, looking at lung cells. And I won't go into what we found there, but it was relatively interesting. But the other thing was that this department also had a contract with a big manufacturer of the NMR or MRI machines. They were just beginning to be used clinically. So we were one of the first departments to get one of those. And the associate chairman had a physics degree, and he looked at what was going on with how they were trying to capture the signal from the image, or to make the image from the tissues that they were imaging in the MRI. And the engineers were all doing this by approximations. And so he said, and he and I sat down and talked, we said, we should be able to do that from a physics standpoint and get it accurately. So we worked with Bessel functions, and sure enough, we showed that you could do that. And so we gave that to the world because we published it. And so they now, or so at least now they could use that and more accurately tell where the signal was coming from. When I was at that department, I went to law school. After I got my degree, I left academia. I went to Washington, D.C. to see what I could do, combining law and all the science background that I had. And one of the areas that I happened to talk to was the U.S. Patent and Trademark Office. In that office at that time, there was an unwritten rule that you didn't hire PhDs. And I can go into that at a later time. Anyway, there were 3 organic chemists there who were getting a few applications that they could not understand. They were coming from biochemistry, molecular biology, cell physiology. They couldn't understand that stuff. They said, we need a PhD. So they hired a person who had just completed an NIH fellowship over from NIH to the patent office. He worked for a year, turned out to be fantastic. So they decided, yeah, we got to get more PhDs. So I came in the second or third group, and so I was about the 10th PhD to go in. Since that time, biotechnology has really taken off. When I was there, we went from 10 examiners to over 100, and I know there's more than that there now. When you're an examiner, you're given, or it just happens that you kind of emphasize certain areas that you're getting examined in. So my areas were in monoclonal antibodies and in nucleic acid hybridization. I left the patent office after 3 years, decided to go on the other side of the desk and actually prosecute patents. You make more money than you do when you're working for the government. So that was a big reason to do that. I came to Boston because it was either Boston or San Francisco, because that's what, yeah.
I keep on hearing rumors over 25 years that the patent office is years and years behind in all the patents. Is that all true?
Let me finish and I'll come back to that, John, okay?
Okay, thank you.
Yeah, I will. I'll come back to that. Anyway, so with the, where was I? Okay, so I came here to Boston because that was one of the hot areas for biotech. And so I spent my time here in biotech, chemistry, some physics and so forth, prosecuting, mainly prosecuting patents. I didn't do litigation too much. I mean, help them, but I didn't do much with it. I retired several years ago. I'm now consulting out of the house in patent law. But what's happened is that I have been able to go back and think about, read about and so forth, all these scientific areas that I was in. So I try to keep relatively current in most of the molecular biology areas that I can, but every time I get started on one thing, something else attracts me. And so 2 hours later, I'm off to something else. So, you know, I scatter around. I'm a dilettante. What can I say?
That's how we know you had done physics.
What's that?
That's how we know you studied physics.
Yeah, I did. Yeah, I was a physicist for, let's see, 6 years for the master's degree, and then a little bit of physics when I was with the radiology department. Yeah, so maybe 7 years, let's say. The rest of the time in biology or biophysics, really. To John's question, the examiners, okay, what happens, applications come in and they get assigned to the examiners, and there's a certain time frame when they have to be taken up and examined. The applications themselves are not years behind. I mean, not many years behind. They are years behind. When I was there, we were in biotech because we were being flooded with them. We were probably 3 years behind in taking up a particular application. The office tries to get it so that you take up the application in less than that. And there is, I believe now, they're trying to get it all, including in the computer area. They try to get it so that the application is taken up within 1 year or 2 years, if it's possible. If it's more than that, that's an unusual situation. Once the application is taken up, it takes a while to get through to get either to the patent or it gets abandoned. One of the two things happens. So I think, John, I think that's the answer to your question, isn't it?
I had heard when I was at Raytheon that people had put in patent requests and were waiting forever.
Okay. What may be happening there is not the patent office. It's your people on the other side of Raytheon that's holding it up.
Could be.
Yeah, because what goes on, and particularly large corporations, I learned as an examiner of this, is that the inventors, yourself, have a great idea, you write it up, and you submit it. You don't send it to the patent office, you submit it someplace in your organization. They take a look at it, they massage it and so forth, and they sit on it, and they try to amplify it, or they try to massage it. And so they'll go back and forth among themselves. They may come back to you for suggestions, but they massage it quite a bit. And then they'll submit it. Other places, like in academics, those guys will send it to their departments, like Lita Nelson. She gave a talk here. Her husband is Don, who's in the group. And they send it out right away. They try to get the academic things out to the patent office as quickly as possible. I know the corporations really, particularly the bigger corporations.
The biggest problem that I heard was the concern was that if you came up with a really good idea, you probably didn't want to write it out so that all the competitors knew whatever your good idea was.
Yeah, we can have a talk about that. There is that, and I'd love to talk, have a chat with all of you about that whole aspect. There's pros and cons to that. Mike?
When I was for a long time, I was on the other side with patents. And one of the things that we were told, and I'm curious to know whether you believe it's true, was that one of the worst things that can happen to a patent application is that it's immediately accepted. Because then you're basically vulnerable to challenges later. Whereas if you have to go back and forth a few times with an examiner, the presumption will be that it's been worked over very strongly. Is there something to that?
Oh, that's great, Mike. Being an examiner, I've been in that situation to see what you're talking about. That definitely is a consideration that everybody in the patent field, particularly the litigators, are very concerned about. there's pros and cons to that. I mean, how many of you have actually participated in the application process from the point of view of submitting the application, getting responses from the examiners, and then sending your responses back to the examiners? How many of you had that? 1, 2, only 2. Okay, probably.
You can use the reaction to put an upright hand.
Yeah, I've only seen 2 upright hands. So I don't know if you want to go into this in much more detail. I mean, if the rest of you are interested in it or not. But just briefly.
Maybe what we should do is move on to the other people.
I think you're right.
And this is another item that can be discussed more later if there's interest. And let me just remind everybody that we are constantly updating the list of things that people want to talk about. And Steve can probably refresh everybody's memory by putting out the link to where we show all the items. Well, we have two lists. One is the list of everything that we've got scheduled, which is now out to mid-April, I believe, maybe even late April. And then there's a second list, which contains all the items that we've talked about possibly scheduling, but for one reason or another, we haven't. And we're always looking for people to put things in there on that list as more candidates. So enlarging some of these talks today, like this one, or the one that Carl talked about, or others, are obvious candidates for that. Okay.
Also, John, if you don't mind, since I'm delving into molecular biology a lot, if there's any topics in areas of molecular biology that you guys want to hear about, guys and women want to hear about, let me know and I'll prepare something for it. So, for example, the CRISPR stuff that's going on.
Excellent. Now let me enlarge what he just said there. Some of our talks are by people who already know a subject really well, and they can just talk about it. All I have to do is organize their thoughts. But there are a number of people in this group. Bob Primack comes immediately to mind, who gets interested in something that we talk about having a presentation on, and he just goes off and he researches it, and he gives a great presentation. And there are others that do the same thing. So this group is an opportunity to use your spare time at home to become expert in something that you were merely curious about before. So anyway, with that, George Burnell, are you around? Yes, you are.
I want to bring something up, and let me get organized here. I'll just be a second. My problem is I had too many choices to make, and found that I had too many stories I could tell, so I didn't had a little trouble deciding what to say today. But let me go with this. I'm going to take a slightly different course, but here we go. And growing up in Lexington during World War II, I had a raft of jobs. By the time I entered the Air Force in 1953, I had been paperboy, a store clerk, a cab driver, a civil engineering draftsman, mid-century modern design draftsman. I had packaged Raytheon's Le Havre and Bremerhaven radar installations. And I had a stint at research at the Boston Federal Reserve Bank. And then I was off to the Air Force, where I was an executive officer. When asked, people said, yes, sir, and so it happened. Then I found myself in the production management program with the B.F. Goodrich Company in Akron, Ohio, working the night shift in a department on a union slowdown over work standards. The steward was turning in false timesheets, and I wouldn't accept them. So his paycheck was zero. That got me invited to visit the vice president of manufacturing for the company. I had good records. I read them off to him, and he turned around and picked up the telephone and read them off to the International Union. And he hung up, sent me back off into the plant. The steward came over, and I dictated his timesheet to him while 50 odd workers watched. And that was the end of the slowdown. Everybody went to work. The semi-strike was over, and that was a pivot to the beginning of my career, which essentially is to solve problems and then implement the solution. Then go on to the next problem, otherwise known as a troubleshooter. So the rest of my career, I did not specialize in any particular product or any particular technology. It just got into a mode of having a problem thrown at me, finding a solution, getting it going, and then moving on to the next problem. So in that process, I've worked for 10 companies, made damn near anything you can think of, and also had a consulting business for 43 years. In 1987, one of the unfortunate episodes, we had a $25 million turnaround fund IPO scheduled for August. And that broker went off on a personal episode, rescheduling the IPO later for late October. And if you recall, the market crashed in October. That was a week before our IPO was scheduled. So we were left swinging in the breeze with $25,000 worth of legal fees and no fund. And had that gone off in August, we would have been sitting pretty ready to buy companies and turn them around. So that's one of the sad points. But what I'd like to do, I can take as much time as you want, talking about some of these ventures and what the turnaround was. But before that, what I'd like to do is talk a little bit about what's happening today. And in March, I still have some consulting efforts. In March, all staff went to working from home. I think everybody's familiar with that. But that meant that each of those homes had to be set up with IT equipment and software and learn how to work remotely. The shop went into all the various recommended actions. We spaced workstations where we could, put up barriers, plastic barriers where we could. Everybody wore masks. We had daily temperature daily. Hired industrial cleaning, sanitizing, and business plummeted about 25%. So the employees dropped to a 4-day week. And then everybody worked jointly. It was a team effort. Well supervised, but everybody either in the plant or at home practiced safe practices. So from almost a year ago now, we've had no lost time from the virus. The business has stayed in the black, and there's been no traveling, either for business or for personal activity, by all the employees. And that business has struggled only from the point that a quarter of the business disappeared and will stay away for a while. But other than that, it's functioning, the business is going well. That's for two businesses that are, couple businesses that are local in this geographic area. Then the prospects, what we're looking at now is that we expect a dismal first quarter. Just nothing is recovering yet. The economy is in sad shape. We expect some stability in the second quarter. And then sometime over the summer, we expect things to start. They will look brighter than they will be. It'll be the fall. We'll probably have the kids back in school. We'll probably start having employees coming to work rather than staying remote, at least part-time, maybe half and half, but we'll be working on bringing people back to the office. But the factory will be all in the plant. They will be back on a 5-day week. And the immediate, well, there's two things immediately. The first thing on the way back is that all the inventories will be run down. So the supply lines are going to be stretched as all manufacturers adjust to what inventories and what products need to be built back up to respectable levels. And then the next thing you get, the other thing that you get into is taking advantage of the new opportunities that result from the new landscape. So there's a lot of new product activity or evolution, rather than, it's not like you discovered something, but new applications, new customer requirements. So you need some decent sales effort, sales engineering, and product development. So those are the, start thinking now as to how you're going to operate your businesses on those structures.
Dave Kahn.
I'm an electronics engineering graduate from Lowell Tech, like one of our other members, but it was called Lowell Tech in those days. I was the second class to graduate because the class was started by an MIT professor and Galabinskis, Dr. Galabinskis, and great teacher, great man. Anyway, my story today, as I mentioned, is clues about Raytheon. One of my first jobs out of school was with Raytheon. I worked with them all, you know, in the radars, the Hawk missile, the intercontinental missiles, you know, and with a lot of other companies. I also worked on consumer hi-fi equipment, high-end stuff, which is amazing. So the degree, what I'm really saying is my degree in electronics engineering got me into many fields where these capabilities could be used. I mean, who knew they were going to end up in automobiles later on, you know, and automate the TVs and do this and do that. So you remember one of my talks on nuclear power. The reason why I went into the nuclear business was because the control room was supposed to be electronically controlled. And the only thing I'll say about that, everybody screwed up on that one. We forgot about changing the the systems in the control room from analog to digital and prioritize them. Because in the fossil days, it didn't make a big difference. If some alarm went off, you didn't have that many. But when you had nuclear power as the heat for the tea kettle, that's a different story altogether. And that was the major problem, or second major problem of what happened, you know, later on in life. But to get to my experience with the local companies here at Raytheon, I worked there twice. I worked there for the Missile Systems Division. You know, for many years, I worked on the Hawk program. I went down to Huntsville, you know, to Redstone Arsenal and trained people there and fixed it and maintained it. Went to Bedford and helped design going from vacuum tubes to solid state at Bedford and doing that. And I will tell you, while we were at Bedford, they were trying to elect a pope. Well, we elected a pope in the lab because white smoke came out of the speed gate all of a sudden. And I mentioned, hey, well, we're electing a pope. I've never seen so many people run like hell and pull the plug out.
I'd love to have a talk on vacuum tubes at some point. I never did.
We would take, I mean, the vacuum, as a matter of fact, the drawings to represent the vacuum tube were about 1 inch in diameter, and the sub-miniature vacuum tubes were like about 1/4, 3/8 of an inch thick and 1.5 inches long. But anyway, that's beside the point. The issue that I want to get to is later on in life, I became an engineering representative and was assigned to the Waltham facility where they make the tubes. And I was working for ITT Gilfillan, and they're from California, and they wanted me to go and work at the Raytheon Waltham plant because the crossfield amplifier tube that was being used in the system was not consistent. It was giving them problems. And they actually showed me a letter from DOD to ITT saying that they got to fix that system. So that was a political job too, going to work at as a engineering rep. But I got along fine, you know, with everybody there. As a matter of fact, the general manager told his guys, "This man is ethical. He has free run of the plant. Treat him like one of us." And that's how I was treated, and that's how I treated them. If I saw something that shouldn't go anywhere, it didn't go anywhere. It stayed with me. And in the long run, there were 2 or 3 things that I found quite surprising. The crossfield amplifier, you know, it's a big object, but yet the cathode, the tube itself, is a piece of jewelry. And after listening to all the problems, I said, look, we got to go through all the drawings. I said, because from the story I get, the guy, and it's not an assembly line. It's more like a prototype lab. You know, they do certain things. So anyway, we went through all the drawings and we found 6 places where the dimensional analysis, you know, you could interpret it one way or the other. Now, when you're working with a cathode, it's electromechanical device. You got to be precise in your math and your physical dimensions and dimensioning also. So that was one. And so we found some issues like that and we fixed them. So when they started making them and testing them, they found that there was continuity because they made in small batches. And it worked out fine. But then I asked another question. I said, the people down in the prototype area, do they have any process sheets to work on? And they said, what's that? So, you know, being a guy, my background, as I said, was electronics engineering, but I like to get my hands dirty. I learned all about assembly and, you know, the configuration. I learned how all the utilities like producibility comes into play from your original design. So I took and applied my knowledge from concept to production, and I was applying it right here. So anyway, no, they didn't have any. So I went down and I talked. The engineer actually asked me, he says, Dave, would you go up and talk to our industrial engineering manager and tell him what you just asked me? And I did. And I told him, look, you know, exactly what I wanted. I says, I want the heat. In those days, we used to call them Heath kits. You know, how do you build these things? The old Heath kit, you know, they were good. So they started that. Lo and behold, I got a compliment from ITT and the Air Force, or who it was, you know, the Navy, because it was the SFC-3. You know, it was a system like the Aegis, where we had a 50,000 watt peak radar, you know, and that thing had to work. So anyway, problem solved. While I was doing this, ITT was wondering if somebody could, if I knew anybody that could make canned oil capacitors or transformers, whatever they want to call them. I said, yeah, I said, they can probably do that here in Waltham. Okay, Waltham bid on it and they got the contract. And now these were drawings from the ITT prototype group, so engineering group. So that should give you a warning. I don't think those drawings ever went through an industrial engineer, because when we tried to build these things in the you know, in a facility, they would pass one test, you know, one pressure test, but they wouldn't pass 2 pressure tests. To make a very, very long story and aggravating time, because we had to do an analysis of all the drawings, what was going on. Well, I found that they were trying to weld or to fabricate a box with dissimilar metals. And in those days, you had to use the blowtorch because the 1,000 watt soldering iron was going out of style very quick. You couldn't buy the damn things anymore. So my company actually told me to shut up. But I'm there working with these people, and I'm seeing that they're following the ITT drawings to the T, and I'm with them. So it had to be an error. So what happened is they got a new program manager, and he hired a new mechanical engineering team when we went through it. And he says, Mr. Khan was right. There were some significant design flaws in the package that we sent. And you know, the other point is that if you gave that job to a small company, it would have put them out of business, because Raytheon spent a hell of a lot of time trying to fix that problem. You know, they were believing the drawings, and I don't believe the drawings, because when I learned in school, well, you don't believe everything you see, read, or hear. You got to analyze it for yourself, and that's exactly what I did. And I found issues and solved the problem. Now, the other thing that I want to talk to you guys is about is going from you know, the power supplies to run these things were vacuum tubes. Well, they wanted to use solid state devices to supply a high power. And I went to a meeting, I didn't know what the meeting was, what they were going to talk about. And then I heard them arguing, well, how do we measure 1 volt? Well, being the wise guy I am, I almost told them to go get a VOM, But that wasn't quite the case. Then they said, well, we need to measure it down to about 4 or 5 zeros. Oh. So what happened there is we had to use a bridge, and we got the the Bureau of Standards, the Standards Bureau came in and worked with Raytheon and ITT and whoever else made high power radars to come up with a method of doing it, because everybody found out real quick that solid state devices aren't as forgiving as the old vacuum tubes. So I guess my story is that engineers, God bless us, sometimes don't communicate the right information to the right people at the right time. And so what if we have another engineering discipline look at our drawings, for producibility and stuff like that, That's my story about Raytheon. I mean, they actually had a double whammy. ITT gave them lousy drawings, and their industrial engineering group didn't get off their butt, and do their job to make the prototype area, more efficient in making these things, because you don't manufacture these. It's just like building an airplane. It's 1 or 2 at a time.
The one person who's left is Dan Klepner.
Look, it's just an incident which took place at college, but it changed my career. I went to Williams College, which was a wonderful place for me. I started out as a freshman, and to my surprise, I did better in physics than I expected to do. So I was really enjoying life there as a sophomore. But I was very concerned. Williams is a fraternity school, and I didn't realize just what the nature of that was or what it meant. What it meant was characterized by an observation going through one of the parking lots there. There were some very flashy sports cars and a lot of old heaps. It turned out the sports cars were owned by the students, and the old heaps were the properties of the faculty. That sort of imprinted in my mind the difference between these 2 populations.
And now you're a professor?
Yep. This is another world. The faculty was really superb. That I had many excellent teachers and became very close with a few. And I was concerned about the nature of the fraternities in the school. The rationale for fraternities really was exclusiveness. They like to be able to select their own group and give them housing and all their social life. I felt that was terrible, that the university or the college had an obligation to provide a decent social situation for all the students and shouldn't leave it up to private groups. And I knew the faculty agreed on this too. It was really a rather anti-intellectual atmosphere there. So in my sophomore year, I screwed up my courage and went to speak to the president of Williams. James Finney Baxter III was his name. And from an old New England family, the Baxter State Park is the Baxter family. And I went to inquire what the administration was planning for the future of fraternities. I was sure they were planning to eliminate the system because it was so obviously detrimental. But it turned out that he thought fraternities were great. He thought the soul of the college was the fraternities. And at that point, I felt I really ought to get out of there. Now, this was in the middle of my sophomore year. there was no opportunity to transfer to another school at that time. But I did want to leave the place just on principle. I'm not generally that dedicated to principles, but I was young and felt this was a moral problem. And my faculty mentors there understood this, and we discussed it. I came up with a plan for leaving well, originally I wanted to spend the junior year abroad, but that wasn't a possible program. But came up with a scheme for graduating a year early. So I would miss my senior year, but only need to be there 1 year more. This involved taking extra classes and having a full schedule and taking the minimum of the physics major. But we would do this because I'd be graduating a year early and could make up any deficits later on. Anyway, this got the approval of the administration. So we went and did it. I took extra courses and such. And the next year I applied to Harvard in the fall and got accepted there to come to do physics. But at the same time, I got awarded a Fulbright fellowship to go to England. And I grabbed at that and went to England. And it was a wonderful experience there. I went as an undergraduate, not as a graduate, which was a good thing to do because the undergraduate life in England is a delightful life. The Cambridge philosophy of education is just put the students together with other rather interesting students and make life as pleasant as possible. And it was mighty pleasant. Met my wife there, and I studied physics there. In my tutorial in my second year, I was there for 2 years. My tutor happened to be a physicist working on what was called molecular beam magnetic resonance. And he discussed his work with me, which was very nice because at Cambridge, the faculty and students were quite isolated. But one of the things he told me was about a suggestion by I. Rabi that you might be able to use magnetic resonance for making an atomic clock, and that the clock might be good enough to measure the gravitational redshift. And that idea really was astounding to me. The fact that you could observe the effect of gravity on time itself. Didn't do anything about it at the minute except tuck the idea away. But the next fall, I went to Harvard and started working with Norman Ramsey, who is a very distinguished molecular beams physicist. And he had a new idea for using the techniques for making an atomic clock. And I worked with him on that. That was called the hydrogen maser, which became a useful atomic clock. In fact, the atomic clocks became much more useful than anyone thought of at the time. They led to the GPS system. The maser was eventually used to observe the gravitational redshift in a lovely experiment, which was completed around 1980. And since then, this gravitational redshift is not just an object to be detected, it's something that you have to contend with very closely. Anyway, so my career got launched by my dissatisfaction with Williams College. And sticking my neck out to leave the place early and go to England turned out to be a very happy choice.
So you ought all to fraternities.
I was very much opposed to fraternities, yes. And I wasn't in a fraternity. There was a club there for people who didn't fit into fraternities called the Garfield Club.
When did they get rid of fraternities? Because they certainly did.
Yes, they did. It was about 4 or 5 years after I graduated. They had a new president, and he came in, I think, with a mandate to get rid of the fraternities. Although Baxter loved fraternities, I think the trustees were wiser than that. And they eliminated them rather easily. I mean, there was some protests, but the fraternity houses got turned over to the college. There's a large bunch of white elephants they had. And then a few years after that, Williams became coeducational. So it's now really a much better school than when I was there.
One of the issues, though, with fraternities, I know at MIT, 50% of the students when I was there were in fraternities, and there was no room in dorms or local Cambridge apartments for people if they didn't have the fraternities. And
Yeah.
it took MIT 50 years to figure out how to solve that problem.
Yeah, no, I was aware of that when I went to MIT. The MIT fraternities were not like the Greek fraternities. The MIT fraternities were always trying to recruit students because they needed a minimum number to make the places work. So they were not as socially undesirable as the Greek letter fraternities at Williams. But I do think it was a failure of MIT to provide housing for these students. And they've been gradually doing it, building dorms for them. So that situation is ameliorated. In any case, MIT does not have the reputation of being a Playboy school. So.
What? Not anymore?
Yeah.
In 1966, Playboy sent interviewers to MIT to interview a bunch of us because they wanted to write an article about MIT, the party school.
Uh-huh.
And I don't think it ever got published.
Yeah.
John, the other half of that story is that whole survey went out and Playboy wrote it all up, and the people from the University of Wisconsin complained because they weren't listed. And Playboy's response was they didn't want to put professionals with amateurs.
Oh, well, okay. So look, it's 11:37. I want to thank everybody for what they did. I would like to get some input from those who talked and those who didn't talk about whether or not we should do more of these. I generally think we should. I think they're fun to do periodically. And there are a few other stories that were planned that didn't get in, and some of them will just stick into a potpourri. And I think that most of the stories we heard today are eligible for a part 2. So we'll deal with that if the folks are interested. But send me your thoughts. So thank you, everyone. And
one parting question, John.
Yeah.
I heard several people today making reference to University of Lowell, UMass Lowell. They happen to have the second best rubber and plastics chemistry department in the nation. And if anyone here has had that course or knows anyone that has that course, I'm looking for someone for a little project.
Okay, wonderful. So let's see, everybody have yourself a wonderful New Year. Just do it by yourself or Zoom or however you're going to do it.